So here's the first of our integrals, and I really just wanted to have done this with you so as to make sure that this integral is at the front of your minds, and it's one that I think people ought to know off by heart, and the answer is sec of theta plus, of course, an integration constant. And the reason why this is the case is because the derivative of the secant of theta is sec theta times tan theta. So therefore the integral of this is equal to the secant of theta. And we're going to use that in both of the other questions. So let's look at them now. So for this question, I think the natural way to perform the integral is to realise that secant squared is the derivative of tangent, and here we have a power of the tangent. So we have a function, the tangent function, raised to the power of 3 multiplied by the derivative of the function. And if we spot that pattern, then we can just write the answer down. So it's going to be equal to, and it's going to be the function, the tangent in this case, raised to one higher power. So we could put brackets around it and write to the fourth, or as I'm going to do, I'm just going to write to the fourth here. And you see I've left a space here. So let's think about what we need to get this right. If we differentiate this, we will bring a factor of 4 in front, which we don't have. So we're going to put a factor of a quarter in front to mop that up. And then when we've differentiated it, the 4's will go. We will reduce the power by 1. We will have tan cubed. And then from the chain rule, we multiply by the derivative of the function that was raised to the power. So we multiply by the derivative of tangent, and that is sec squared. So this is up to the integration constant, correct? And we know that this is right. Again, you can just pause, think about it in your head, convince yourself, yes, this is right by differentiation. Now, just for the fun of it, I'm going to perform this integral in a slightly different way. So what we could also do, and this is not as natural, but it's going to help us with the next exercise, is we could say, well, this integral is equal to the integral of sec theta times sec theta tan theta tan squared theta d theta, and this is the derivative of secant, and this can be rewritten as powers of secant from our favourite identity when we see tangents, that tan squared is sec squared theta minus 1. The way I remember it is that sec squared theta is greater than or equal to 1, and it's equal to 1 plus tan squared theta. That's the way I remember the identity, and then you just rearrange it in this way. So our integral is equal to the integral of sec cubed theta minus sec theta, brackets around it. And what I've done here is I've taken this and I've multiplied it by that. And then this is multiplied by sec theta tan theta d theta. And that is this. So this is definitely not the way I'd perform the integral. I would do it this way, but I just want to show it leads to the same thing. So let's have a look at this. What we have is powers of secant multiplied by the derivative of secant minus a power of secant multiplied by the derivative of secant. So in exactly the same way as here, we can just write down these effectively two integrals because of the subtraction here. So what we obtain is equal. So I'll just leave a bit of a space, and then we're going to increase this power by 1. So you'd have sec to the fourth of theta, and then when you differentiate that, what are you going to get? So we get sec to the fourth of theta. So just looking at the first integral here, this one. So if I differentiate that, I would pull down 4 sec cubed and then multiply it by the derivative, which is sec tan. So I just need to put a factor of a quarter in front. And that is our first integral. And then we subtract. And now this is sec to the power of 1. So again, we increase the power by 1. So it's sec squared theta. And we need to put in front a factor of a half. And again, let's just pause, think about it. You differentiate that. The 2 comes in front, cancels the half. Reduce the power by 1, you get secant of theta. And then from the chain rule, you multiply by the derivative of sec, and that is sec tan. So this is our answer for the integral, plus of course an integration constant. And now we look at this, and we look at this, and they don't look to be identical. So what's happening here? Well, what's happening is that we are using the identity here again, and there is going to be a difference, but the difference is a constant, and it's therefore hidden in the ambiguity of the integration constant. I've just written plus c in both cases, but that doesn't mean that they're the same constant. I'm just saying it's up to a constant. So a nice thing to do is to take this, I'd start with this because it's simpler, and show that this turns into this. So let's just do that. So what we have is 1/4 tan to the fourth of theta is equal to 1/4, and it is sec squared theta minus 1 all squared, because tan to the fourth of theta is tan squared theta squared, and tan squared theta can be written in this way. And therefore we just expand it. We have a quarter, open brackets, and when we square this, we're going to get sec squared theta squared. So that's sec to the fourth of theta. Perfect. That's the term we have here, a quarter sec to the fourth of theta. We're going to get the cross terms, and they're going to be multiplied by 2. So we're going to get minus 2 sec squared theta. And then we're going to get plus 1. And that is, of course, a constant. And you can see if you tidy this up, a quarter times minus 2 is minus a half sec squared theta. And this term is essentially irrelevant because it's a quarter times 1, it's a constant, so it's just hidden in the ambiguity of the integration constant. So we can see that these two results, this and this, are the same for the integral up to an integration constant. So everything is working. Okay, as said, this is how I would perform this integral. This is really just for fun. But this idea is going to be useful for the next integral, which let's look at that now. So in this integral, what we see is that we have secant cubed times a tangent. And secant cubed can't be written simply as secant squared, the derivative of tangent, times powers of tangents. What you would have would be secant squared times 1 secant, which is the square root or plus or minus the square root of tan squared plus 1. And that's not going to be an easy integral. So instead, the way we calculate this integral is as follows. We just rewrite it as the integral of secant squared theta times sec theta tan theta integrated with respect to theta. And now what we see is that we have got powers of the secant times the derivative of secant. So therefore we can immediately, again by inspection, write the answer down. So what we're going to do is increase this power by 1. So I'll just leave a bit of a space here. And then we're going to write secant cubed of theta, increase the power of secant squared, plus some integration constant. And now, if we differentiate this, we'll pull a 3 in front. We don't have that here, so that's easy. We'll just put a factor of 1/3 there. And then what we do is the 3 and the third cancel. We reduce the power by 1, giving us secant squared. Good. And then from the chain rule, we multiply by the derivative of secant, and that is secant times tangent. So that is our integrand. So as soon as we see a single power of the tangent multiplied by powers of the secant, this can be performed, and this gives us the integral. And with that, I'm going to essentially stop the video, but on the next slide I'm going to give you some questions which can be performed using the methods I've gone through in this video, and I will also give you the answers so you can check that you've got them right. So here are 3 problems for you to integrate, and what I will do in a moment is write down the answers, but I'd suggest you pause the video, try and do them on pen and paper, and then come back and check the answers. Okay, so I'm about to write the answers down. Here they are. So the first exercise, we notice that this is the derivative of tangent. So what we're going to get is an increased power of the tangent. So it's going to be something like tangent squared of theta plus c, and there will be a factor of 1/2 in front of it. You could also perform this one using the method I just described, and were you to do that, what you would obtain is 1/2, and it will be sec squared theta plus c, and the difference between those two results is purely a constant. The next integral, what we notice is that there is a single tangent here, and we can rewrite this as a power of the secant times sec theta tan theta, and if you do that, what you are going to obtain is the secant to the same power that we had here, and what that gives us is therefore 1 over the square root of secant of theta plus an integration constant. And let's now just think about the numbers. If you differentiate that, this is to the minus 1/2. So you will pull out a factor of minus 1/2 in front, and that means that we're going to need a power or a factor of -2 to sort that out. And again, I'll let you check that the details are correct here. And then finally, this integral I would say is very easy because this is the derivative of tangent. So therefore, we just need to increase this power by 1, and we are going to get tangent of theta to the 3/2, and there will be a factor of 2/3 plus an integration constant. And with that, I will stop this video.